Hi, this is Neil Feit from the Philosophy Department at SUNY Fredonia. In this video, I'm going to be talking about truth tables for the operators of statement logic, sometimes called sentential or propositional logic. We're going to talk about determining the truth value of a compound statement, given that we know certain facts about the values of the statement letters, the atomic statements that it contains. And we're also going to use some truth tables to find out if a given argument is valid or invalid. If you're using the Power of Logic book, this video supplements section 7.2 and also section 7.3 of that book. Okay. In our book, or the system that we use here, we use the dot for the AND symbol, and some systems use either an ampersand or a symbol that looks like that, a caret. We use an arrow for conditionals if then. Sometimes you'll see a horseshoe kind of symbol, and for a biconditional, double arrow, sometimes you'll see a triple bar symbol like that. Okay. In a very real sense, these tables give the meanings of the logical operators in statement logic. For example, the dot symbol, to say what it means in statement logic, it's just a symbol that when it comes between two true statements, for example, yields a true compound statement, or in all other cases it yields a false statement. Okay? So in a very real sense, the operators are defined by these basic truth tables that you see here. Okay, this makes the operators what we call truth functional in statement logic, and that means that the truth value of a compound statement containing these operators is entirely determined by the values, the truth values of the components. So for example, if you know whether the atomic statements are true or false in a given compound statement, however big it is, in theory you could just compute the value of the entire statement. We could actually contrast that with an English statement operator like the word because. Okay. For example, if I have like a true statement, because another true statement. Okay. So for example, the reason I put these question marks here is, suppose I say something like this. Suppose I flick a lighter and a flame appears. Okay. Well, this statement might be the flame appears because I flick the lighter. Okay, and that is a true compound statement with a true input P and a true input Q. Okay, in other words, the flame appeared because I flicked the lighter, and that's true. However, a true P and a true Q might also give a false statement here. For example, if I suppose T is George Washington was the first president, and this other one here is Obama was elected president in 2008. If I say something like George Washington was the first president because Obama was elected in 2008, well, that's going to be false, even though still I have a true P and a true Q. Okay, so the because operator in English is not truth functional. Just because we know the values, if all we know is the values of what's on either side of the because, that doesn't give us enough information to determine the truth value of the whole compound statement. It could be true or false depending on the content of the P and the Q in this case. But the operators that we're going to be working with in sentential logic, statement logic, are truth functional operators, and that's going to let us do certain exercises in statement logic. So I'm going to work on a few exercises that have us determine the truth value of a compound statement. I'm going to do 7.2a. I'm going to make a choice here. I'm going to do number 14 first. I'm going to scroll down and generate my quiz. Okay. The instructions here tell us to make certain arbitrary assumptions. We're supposed to assume that A and B are true statements, C and D are false statements. Okay. What I'm going to do here is I know that C is false according to the instructions. I'm going to write that under C. I know that A is true and D is false. Okay. The main operator of this statement is the first arrow, And it's important to be able to recognize that, because here we're going to work from least main to the main operator as we kind of compute the truth value of the statement. So here I have A arrow D, which is a true statement, arrow a false statement. Well, that's going to be row 2 of the conditional truth table that I showed before. If you want to go back and look at it, feel free. A true arrow false is a false statement. Now, I'm going to use this false statement as the consequent of the main operator. So this statement, most fundamentally, is a falsehood, arrow a falsehood, which is going to be row 4 of that truth table. For the conditional, it's going to be true. Okay, so if I select true here and check my answer, I'm going to expect that it's correct, and that is the case. Okay, I'm going to do another one from 7.2a. I'm going to go down to number 15. Notice that the only difference between 14, which we just did, and 15 is the parentheses. The parentheses are around the first arrow, so to speak, rather than the second arrow. Let's see if that makes a difference. Okay. So here, again, we're to suppose that C is false, A is true. I'm just reading the instructions. D is false. Okay. Here, however, the main operator is the second arrow, so we're going to compute the first operator first, and a false arrow a true is true. So now the whole statement is a conditional whose antecedent is true and whose consequent is false. Well, that's false, which is different from number 14 that we just did. So if I select false here for the answer, I'm going to hope that that's correct. And it is. Okay, so parentheses make a difference. In this case, changing the placement of the parentheses changes a true statement into a false statement. I'm going to choose another one from 7.2a here before we kind of move on a little bit. I'm going to choose number 21. I chose this not because it's difficult or challenging, but one of our permissible departures from strict grammar in statement logic is that even though parentheses are official grammatical symbols, we sometimes use square brackets just to make certain things easier on the eye. So for example, in this case, the square brackets kind of make it easier to pick out that the first tilde there, the tilde, is the main operator of the statement. This statement is fundamentally a negation. It's a negation of a conditional whose antecedent is a statement letter and whose consequent is a disjunction. Okay, so I'm going to use the same assumptions here. A is true, C, according to the instructions, is false, B is true. Okay, and I'm going to just compute or determine some truth values. Again, I'm going to work from the least main to the most main operator. So I'm going to do this disjunction first. False or true is true. That's row 3 of the V truth table, if you want to go back and take a look. Now we have a conditional to deal with, a T arrow T conditional, which is T. Okay. However, we are negating that. So the negation of a truth is a falsehood. So if I key in false for this statement, I should expect that answer to be correct. And it is. Okay. So one thing is that the fact that our logical operators are truth functional, in other words, that the truth value of any compound statement that they form is entirely determined by the values of the simpler statements and ultimately the statement letters, the atomics, is very important to doing this kind of thing. And second, it's very important that you know the basic truth tables for the operators in order to do this kind of thing, and that's going to be a very important ability to have under your belt when dealing with statement logic. I'm going to talk about one other thing before leaving 7.2 material here, if I may. Briefly scroll down a little bit. I'm going to add a little bit of information here. Suppose, just like in those 7.2 exercises, A is true and C is false, But suppose that we don't know the value of x, okay? In statement logic, which is classical logic, any statement is either true or false. So here, just suppose that A is true and C is false, but we simply do not know the value of x. And the idea is, given that we don't know the value x, can we or can we not still compute or determine the value of this compound statement? Okay. So for example, I'm here told that C is false, and I don't know what x is. I'll put a question mark. Okay. However, if I know anything about the truth table for the dot, I know that a falsehood dot anything is false. The only way a dot statement can be true is if both sides are true. So when I take that falsehood and I negate it, I know that this statement is true, despite the fact that I have no idea whether x is true or false. So even if there are some unknown values, we can still compute the truth values of certain compound formulas. And this is, again, due to the fact that the logical operators of statement logic are truth functional. Okay? I'm not going to go through this in detail, but even though I don't know what x is, and I don't know what x is, okay, I still know that x arrow x is going to be a true statement no matter what. Okay? You can pause or look at a truth table. If you look at the arrow truth table, the top row, row 1, and the bottom row, row 4, you'll get an idea perhaps of what I mean here. However, we can't always determine the truth value of a compound statement, given that we know some but not all of the values. So if A is true and x is unknown here, okay, I can't determine whether the compound statement here is true or false. Okay, if x happened to be false here, the whole statement would be false, t arrow f. But if x were true, the whole statement would be true, and we'd have t arrow t, which would be true. Okay, so in some cases, what's important is that you can determine the value of a compound, for example, even though you don't know the values of some of its parts, or any of its parts for that matter, but in some cases you can't. This is going to end the discussion of 7.2, and I'm going to go on to 7.3 in the Power of Logic book here. What I'm going to do is do a couple of truth table tests to evaluate arguments for validity. Okay, I'm going to first choose a number 9 here of 7.3a. Alrighty. Here's an argument. This one has two premises. I'll draw sort of a box around the first premise. Okay, the first premise says A or B, and it's not the case that A and B. If that strikes you as an exclusive or, that's good. It basically says A or B is true, but not both. The second premise says that A is true, and the conclusion says that therefore B is not. B is not true. So this should strike you as a valid argument. Okay. We could use truth. What I just did was left-clicked in the box there to give me a cursor. And basically what you do here is what's called a joint truth table for the argument. What I'm going to do is, since premise 1 here is compound, I'm going to fill in a truth value under all the operators. Okay, and basically I'm going to do this main operator last. Okay, I'm going to do this v first, do this dot second. It doesn't matter. I could really do that first. I'm going to do this third. And this main operator I'm going to do last. Okay, we're working from innermost parentheses to outermost parentheses. Okay, I'm going to space ahead a little bit. A and B is also true in row 1. I'm going to do a back left arrow. That's false. I'm going to delete to keep things lined up. You don't really have to keep things lined up for the program, but I really like to do that. So in row 1, we have a t.f, which is going to be an f statement, right? Are you with me? Okay, for the first premise. I think I'll do the first premise first. One thing that I actually like to do is I actually like to work in columns rather than rows, and to some extent this is a personal preference, but I know here that the thing I'm working on here is A or B, and I know that's going to be TTTF, so that kind of makes it a little bit quicker for me. TTT. F, okay. And here I'm working on A and B, And I know that's only true in the first row, TNT. Otherwise, where there's at least one false statement, it's going to be F. So it's going to be F. And I'm keying in capital letters here, and I'm using the space bar to move around after I click in the field. Okay. Now I'm simply going to negate that. What's the negation of F? T. And maybe I'll delete to keep things lined up, although that's not essential, but it is easy on the eyes. I'm negating the F here. Okay. All right. Now what I'm doing is I'm taking this column and I'm taking this column and I'm going to do the main operator column right here. Alrighty? So I'm doing the conjunction of a T and T. T. I'll hit delete. T. And here I have a false conjunct on the left side, so that's going to be false. So there's the truth table for the first premise. Okay. Notice that I'm putting in values, truth values, T or F, under the operators here only, and not under the statement letters. But here, in the second premise, the premise happens to be a statement letter. Okay? If that's the case, if a statement letter is either the premise or the conclusion of an argument, this program wants you to put in the relevant values. So I'm just copying the base column A here. If you look all the way to the left, the column under A, T, T, F, F. Okay? But the conclusion is compound and negation is compound. So I'm not going to put a value in for B. I'm just going to put in a value in for not B. So it's going to be F in row 1, T, F, T. Okay? So basically what I did was a truth value for the first premise, a truth table rather for the first premise, a truth table for the second premise, a truth table for the conclusion, thus creating a joint truth table for the argument. I'm going to check it. Okay, it says my truth table is correct. What's important now is how to use the truth table. Okay, basically, a truth table for an argument shows that the argument is valid if and only if no row has all true premises leading to a false conclusion. Okay, so basically we are looking horizontally here, but we're actually only focusing on the main operators. And there's no operator here, but okay. So in row 2, for example, we have true premises, but we also have a true conclusion. So that's okay. In row 1, we have a false premise here. In row 3, we have a false premise. Row 4, we have a false premise. So we never have a row. We never have a row where truth in all the premises leads us to falsehood. Okay? That makes this a valid argument. Alrighty, that's correct. So if you know how to do a truth table for a statement, you basically know how to do a truth table for an argument. And if you know the definition of validity in statement logic, that an argument is valid provided that no row in its joint truth table has all true premises and a false conclusion, you could do this test. And it really is sort of a decision procedure. It's a yes or no test that, given any statement logic argument, is going to deliver a yes answer if it's valid or a no answer if it's not valid. I'm going to do just one more. I'm going to do a 7.3b exercise. Let me do number 14 here. Okay, this argument has only one premise, and that's fine. Not every argument has two premises. Some of them have 3 or 5 or 17. Some arguments have only one premise. This argument has 3 statement letters, H, B, and S, so we'll need an 8-row truth table, 2 to the third power, 2 truth values, TF, to the third power, 3 statement letters equals 8 rows that we're going to need here. Okay, so I'm going to left-click or right-click if you're a lefty using a lefty mouse. And what I'm going to do here is H and B. As I look down here, H and B are both true in the first 2 rows, but all the other rows have one of them being false. So I quickly know that this is going to be true, true, but then it's going to be 6 more falses. And I could do that pretty quick. I'm a column kind of person. If you're a row kind of person, that's great. Okay? And now what I'm going to do is I'm going to take my column that I just did, and I see here that the consequent of the conditional is S. So I'm going to look at my S column, And I'm simply going to write down under the arrow the result of doing an if as the column that I just did with a then, a consequent, as the S column. Okay? So in the first row we have T arrow T, which is going to be T. Second row we have T arrow F, which is going to be F. All the other rows are going to be super quick. Do you see why? Whenever a conditional has a false antecedent, the whole conditional is going to be true. Just look at rows 3 and 4 of the arrow truth table. Statement logic is easy in a lot of respects if you know the facts about the basic truth tables, okay? So the column that I just did is the main operator for the premise. Now I'm going to do B arrow S. I'm looking at the B base column, I'm looking at the S base column, and I'm going to do the arrow truth table. Here in row 2 we have T arrow F. We have an F antecedent in 3 and 4. Here in row 5 we have a true arrow true. Here we have another true arrow F in row 6. You get it? That's the only way a conditional is false. Here we have F arrow T, true. And in row 8 here, F arrow F, true. Okay? So that's just the grunt work of filling in the truth table. One of the nice things about this is it does give you feedback. If you make a truth table mistake, it'll tell you. Okay. What I'm going to do here, before I finish up, I'm looking at the main operator here, and I'm looking at the conclusion. Okay. This argument is valid provided that there's no row in which all false premises, here we have only one premise, all false premises lead to all true premises lead to a false conclusion. So I'm looking for rows that might show this to be invalid. Here we have a true premise, it goes to a true conclusion. I'm scanning down. Row 6 is this? We have a true premise leading to a false conclusion. Okay, row 6, the row that the horizontal row, which we are looking at here, that I just kind of highlighted there, is a row where we have all true premises, in other words, all one true premises, leading to a false conclusion. So that row shows that this argument can take us from true premises to a false conclusion. And I'm going to check that row here and click the invalid tab. Okay, and it tells me I'm correct. Row 6 shows that this argument is invalid. Alrighty? So, in a nutshell, in statement logic, an argument is valid if and only if there's no row where all premises are true and the conclusion is false. If there is such a row where all premises are true and the conclusion is false, the argument is going to be invalid. So we have here a sort of a yes or no decision procedure for testing arguments for validity in statement logic. And it might make sense to you that this argument is invalid. Suppose H is I'm happy, and B is it's my birthday, and S is something like I sing a special song. So the premise here is if I'm happy and it's my birthday, then I sing a special song. Does it follow then that if it's my birthday, I sing a special song? Well, you could probably see that that doesn't logically follow. Maybe if it's my birthday and I'm really bummed out, I'm not going to sing a special song. So anyway, I hope this video was helpful to you, and I'm going to sign off for now.